Hello and welcome. Tonight we're wandering into a story about motion, gravity, and the simple, steady rules that hold the universe together. Don't worry, I'll try not to make it too fascinating. After all, the goal is rest, not a physics exam. Think of this as a bedtime story about apples, orbits, and the quiet man who spent more time thinking than talking. Before we begin, take a moment to like the video and subscribe. But only if you genuinely enjoy these sleepy science journeys. And if you're still awake at the end, I'd love to know where in the world you're listening from and what time it is. It always feels a little magical, imagining these words traveling across time zones like a faint ripple of starlight. Now dim the lights, maybe let the soft hum of a fan or some night sounds fill the air, and let's begin. Picture an orchard. The air is still, the grass slightly damp with evening, the branches heavy with apples. Not the shiny supermarket apples we know today, but small, irregular, perhaps a little spotted. They hang quietly, waiting, until the tug of gravity and the loosening of stems conspire to let one fall. You hear the faint thud as it strikes the ground. Nothing dramatic. Apples have been falling since apples existed. But for one man, Isaac Newton, this sound was not just background noise. It was a question. Why did it fall? Not in the vague way children ask, "Why is the sky blue?" but in a sharper sense. Why downward? Why not sideways or upward or hovering halfway? Why does the apple fall to earth and not earth to the apple? Or perhaps, does it fall both ways? The famous apple story has been polished by centuries of retelling, embroidered with details Newton himself may never have claimed. It was not a sudden bonk on the head that sparked genius, like a slapstick cartoon. It was quieter. Newton himself later told visitors that seeing an apple fall in his family orchard reminded him of a bigger question. What holds the moon in place? You drift now between the two images, an apple dropping gently to the ground and the moon gliding endlessly in orbit. Both motions, he suspected, were guided by the same law. A law of nature that whispered beneath every falling leaf and circling planet. But in that orchard, the thought was not yet an equation. It was a seed, a curiosity planted quietly that would grow into the most influential book in the history of science, the Principia Mathematica. For now, though, the orchard is still. Newton was not the type to shout his discoveries or rush to publish. He was a quiet man, prone to solitude, sometimes difficult in company, but gifted with a mind that could sit with a question far longer than most people could tolerate. He turned ideas over and over like a stone in the hand, smoothing them until their edges disappeared. And the apple was not the only stone in his hand. The whole of motion itself puzzled him. Why did things keep moving until stopped? Why did heavy bodies fall faster than light ones, or did they? Why did the moon not simply fly off into space? At the time, the answers were not obvious. Aristotle, centuries earlier, had claimed objects had natural places. They returned to stones to the ground, fire to the sky. Galileo had shown that motion was subtler, that objects continued unless something interfered. Newton would go further still, giving precise form to the intuition, turning falling apples and circling moons into a single set of laws. But here, in this first moment, you can imagine him simply watching the orchard. A young man back home in Woolsthorpe during the plague years when Cambridge was closed, wandering fields, studying light through glass, playing with prisms, and wondering why apples fall. The story is gentle because discovery is not always fireworks. Sometimes it's a fruit, a thud, a thought that lingers. Scientists still debate how literally the apple incident should be taken. Was there truly a falling apple? Or was it just a neat story Newton told later, knowing people loved a good image? Either way, the symbol remains. The apple is not just fruit. It is curiosity, pulled downward by gravity and pulled inward by thought. And perhaps that's the quiet lesson here. Curiosity begins in ordinary things. A falling apple, a swinging door, a ball rolling across the ground. Nothing grand, nothing dramatic, just small questions that grow into laws that describe the whole universe. So tonight, let yourself imagine that orchard. The cool air, the hush of leaves, the steady pull of gravity guiding fruit to the earth. Nothing hurried, nothing loud, just the rhythm of motion, always downward, always steady. You don't need to solve equations. You don't need to recite laws. Just sit in the grass with Newton, let your eyes follow the fall, and feel the same quiet wonder. The orchard holds the beginning. The apple holds the question. And soon, Newton will hold the answer. The orchard fades, its branches swaying gently in the night air, and now you drift further back in time to the beginning of Isaac Newton's life. Before the falling apples, before the laws of motion, there was simply a child, quiet and watchful, born into an England unsettled by civil war. Newton entered the world in 1642, small and fragile, so tiny that some thought he might not survive his first night. His father had already died, and his mother would soon remarry, leaving young Isaac to be raised largely by his grandmother. The household was one of modest means, surrounded by farmland and stone cottages, with the steady rhythm of village life carrying on outside. You drift through Woolsthorpe, the hamlet where he grew up. Stone walls line the paths. Sheep graze. The air smells faintly of hay and hearth smoke. It is not a place of noise or bustle, but of silence. the kind of silence that invites long hours of observation. Newton, even as a boy, was said to be quiet, withdrawn, sometimes lost in thought. While other children played boisterous games, he built things. Windmills out of scraps, kites that carried lanterns into the night sky, simple sundials scratched into walls and wood, marking the passage of hours. You picture him crouched in the yard, tinkering with bits of wood and string, eyes narrowed not in frustration, but in focus. It is the same focus he would carry all his life, the ability to let the world fall away while he followed a thought wherever it led. Scientists still wonder how much of genius is born and how much is shaped. Was Newton extraordinary from the start, or did the solitude of his early life sharpen his inward gaze? Perhaps both. The boy left to his own devices grew into the man who could sit with a problem for years, unraveling it slowly, patiently, until the answer appeared. And though his childhood inventions were small, they hinted at the laws to come. A sundial is, after all, a way of measuring motion. The sun's slow arc turned into shadow. A windmill is a dance between moving air and turning blades. Even in play, Newton was already watching the dialogue between force and motion. You drift closer to the farmhouse at Woolsthorpe, where young Isaac scratches figures into the soft stone walls, tiny carvings still visible today. He may not have known their meaning fully, but he was already practicing the art of marking time, measuring space, recording thought. It's worth pausing here to notice the gentleness of beginnings. The laws that would one day describe planets and comets began with a boy scribbling on walls, flying kites, watching shadows. Not with grandeur, but with curiosity. And perhaps that is something to carry with you too, that the seeds of great insight are often planted in ordinary soil. A child with a stick, a shadow on the wall, a question asked softly into the air. So let yourself rest in this image. The small farmhouse, the wide orchard fields, a quiet boy tinkering by lamplight, lost in thought, already reaching for laws he could not yet name. The child would become the man. The questions would become answers. And the stillness of Woolsthorpe would echo into the very laws of the cosmos. The farmhouse fades softly behind you, and now you drift into the next chapter of Newton's life. The quiet boy has grown, his curiosity still restless, and the world begins to open for him. His path leads to Cambridge, to Trinity College, a place filled with books, scholars, and the gentle hum of ideas colliding in stone halls. Picture the college in the mid-1600s. Cloisters echo with footsteps. Candles flicker in long, drafty rooms. Students pore over texts in Latin, scribbling notes with ink that smudges on their fingers. The air smells of parchment and smoke, of dust and rain-soaked wool. Newton arrives as a student, not yet celebrated, not yet even remarkable in the eyes of his teachers. He is quiet, still shy, but he soaks in the writings of the greats: Aristotle, Descartes, Galileo, Kepler. Their ideas swirl in his mind, mixing with his own private observations. But then history intervenes. The plague sweeps across England, and the university closes its doors. The students scatter, fleeing the crowded halls for safety. For Newton, this means returning home to Woolsthorpe. For most, a disruption. For him, an opportunity. You drift back into the orchard once more, but now with a different atmosphere. Newton is no longer a boy. He is a young scholar, armed with mathematics, astronomy, and restless curiosity. Alone, without the bustle of Cambridge, he begins what would later be called his annus mirabilis, his year of wonders. In this quiet isolation, he experiments with light, passing it through prisms and discovering that white light splits into colors, that the rainbow is hidden inside every sunbeam. He calculates with gravity, testing the idea that the same force pulling apples down might also hold the moon in its orbit. He sketches the early outlines of calculus, a new mathematical language that would allow him to describe motion with precision. All of it in solitude, all of it while the world outside battled disease. Scientists still wonder at this coincidence. That one of the greatest leaps in human thought happened not in lecture halls, but in a small farmhouse during quarantine. Newton himself later wrote that he was in the prime of age for invention. And in those plague years, invention flowed from him quietly, steadily, like a stream swelling in spring. You drift into his small workroom now. A prism rests on the windowsill, scattering colors across the wall. A notebook lies open, filled with neat lines of figures. Outside, the orchard waits, apples hanging, a reminder of gravity's quiet pull. It is almost eerie. How much began here, not with noise, not with acclaim, but with patience. Newton's solitude became the soil from which his greatest ideas grew. And perhaps that is the gentle lesson for us, whispered through time, that isolation need not mean stagnation. Sometimes, in stillness, the mind finds space to wander further than it ever could in company. So rest in this picture. The young Newton at home, the world slowed by plague, his thoughts leaping far beyond the orchard, toward laws that would describe planets, stars, and the very fabric of motion itself. The boy who built sundials and kites was becoming the man who would write the rules of the cosmos. The orchard and the prism fade behind you, and now the story shifts from Newton's quiet life to the first of his gentle laws of motion. You don't need to brace yourself for mathematics. Think of this instead as a bedtime explanation, where everyday sights, a rolling ball, a sliding mug, whisper the universe's secrets in simple ways. Newton's first law is sometimes called the law of inertia. It says, "A body at rest will stay at rest, and a body in motion will keep moving unless acted upon by an outside force." It sounds simple, almost obvious, but in Newton's time it was revolutionary. For centuries, people believed what Aristotle had taught, that motion needed constant effort. Stop pushing, and the object stops moving. Push harder, and it moves faster. To them, rest was natural, and motion was temporary. But Newton, following Galileo before him, saw deeper. He realized that motion itself is just as natural as rest. A ball rolling on a perfectly smooth, endless floor. No friction, no bumps, no air to slow it, would keep rolling forever. It doesn't need someone to keep nudging it along. The only reason things stop on Earth is because forces like friction and air resistance quietly interfere. You drift now into a gentle thought experiment. Imagine a coffee mug sliding across a polished table. At first, it glides, smooth and steady. Then, slowly, it slows, friction rubbing away its energy until it halts. To the eye, it looks like the mug naturally comes to rest. But Newton reminds us, no, it was the table stealing its motion, the air brushing against it. Remove those, and the mug would slide on endlessly, as steady as a star. Inertia. You float into space now, where Newton's law is easiest to see. A satellite, once launched, keeps circling Earth without anyone pushing. A drifting astronaut, once moving, continues drifting until a force, maybe the puff of a jetpack, redirects them. Up here, with so little friction, Newton's law reveals itself in silence. Scientists still wonder how to best explain inertia to beginners because it feels counterintuitive. On Earth, almost everything eventually slows. But once you see the hidden hands of friction and drag, you begin to notice the law everywhere. A car coasting when the engine cuts off. A puck sliding across ice, moving much farther than it would on grass. The Earth itself, spinning steadily for billions of years, with nothing to stop it. Newton's first law is not just about objects. It's also about patience. About the idea that things continue unless interrupted. A kind of cosmic persistence. And there's comfort in that, isn't there? That motion doesn't need constant struggle. That rest can continue as rest, and movement can continue as movement unless something outside intrudes. You drift back now to the orchard, to the simple sight of an apple hanging from its stem. At rest, it stays at rest until the stem weakens, until gravity tugs harder than the twig can hold. Then the apple moves, beginning a new story of motion. The law of inertia isn't flashy. It doesn't roar like fire or sparkle like stars. It sits quietly at the foundation, reminding us that nature prefers continuity. Things go on as they are until nudged otherwise. So let that thought settle into you as well. You don't have to force stillness. You don't have to force motion. Both are natural states. And for tonight, you are allowed to rest, undisturbed, just as surely as a body at rest remains at rest. The quiet apple drops from its branch, inertia carrying it downward. And now you drift into Newton's second law, the one that speaks of how motion changes. If the first law is about the natural tendency to keep going, the second law is about what happens when something nudges that tendency. In Newton's language, force equals mass times acceleration. Don't worry, this isn't a math lesson. Think of it as a whisper from the universe. The harder you push, the more something moves, the heavier the thing, the harder it is to move. You drift into a simple scene. A wooden cart sits on a dirt path. You place your hands against it and push. At first, nothing happens, the cart resists. But with enough effort, it begins to roll. Push harder and it speeds up. Stop pushing and inertia takes over, the cart continuing until friction slowly wins. That's Newton's second law playing out in front of you. Force makes motion change. The stronger the force, the faster the change. And the heavier the cart, the more mass it holds, the harder it is to budge. Now picture the same push against a child's toy wagon. Effortless. A small nudge, and it scoots along merrily. But try the same with a loaded ox cart, and you find yourself straining, your muscles trembling against its weight. The rule is clear. Heavier things resist change more stubbornly. This law isn't only for carts and wagons. You feel it every time you try to stop suddenly on ice, your feet sliding farther than expected. You feel it when you press the gas pedal in a car, and the seat pushes against your back, accelerating you forward. You feel it when you catch a ball, its momentum pressing into your palm, your hand stinging with the force. Scientists still wonder at how simple this law is, and yet how universal. The same formula describes an apple falling, a cannonball flying, a rocket leaving Earth, a comet sweeping around the sun. The pushes and pulls may differ in strength, but the principle hums beneath them all. Force guides change. And this law carried Newton's thinking outward into the heavens. Why do planets curve in their paths? Why does the moon not fly away? Why does a stone, when thrown, arc gracefully to the ground? Each is a balance of forces, mass, and acceleration. You drift now above Earth, watching a satellite being launched. The engines roar below, fire and smoke pushing downward. The rocket responds upward, mass and acceleration trading whispers through Newton's law. Without enough force, the rocket falls back. With the right force, it slips free, coasting into orbit. The same rule that explains your push on a wagon explains humanity's leap into space. And yet, for Newton, the law was not about drama. It was about clarity. A way to write the world's motion in numbers, yes, but more than that, a way to see motion as balanced, ordered, knowable. There's a comfort in that. The universe is not chaotic. It does not move without reason. Every change in speed, every twist, every fall is the result of a force. Push, pull, weight, resistance, all accounted for. So tonight, let yourself imagine this law not as a cold equation, but as a lullaby of cause and effect. Push something gently and it glides. Push harder and it leaps. Heavier things take more effort, lighter things less. Simple, universal, steady. You don't need to calculate. You don't need to solve. Just notice. Every time the world moves, some quiet push or pull made it so. And maybe, just maybe, you can let that ease your own motion now, from wakefulness towards sleep, nudged softly, gently, by the forces of rest. The cart fades back into stillness, your hands no longer pushing, and now you drift toward Newton's third law of motion, the one that speaks of balance. A law not of effort or inertia, but of relationship. For every action, there is an equal and opposite reaction. Simple words, but within them, a symmetry as quiet and profound as any poem. Picture yourself leaning from a small rowboat to scoop water with your hand. You push the water backward, and the boat drifts forward. The action and its partner are inseparable, two sides of the same coin. Or imagine a bird in flight. Its wings push air downward. The air pushes the bird upward. The bird soars, but only because it has pressed against the sky. You drift now to the banks of a river, watching a fisherman pull on his oars. Each stroke presses water back, and in reply, the boat glides forward across the current. Push and push back, perfectly paired, perfectly fair. This is Newton's third law. Motion is never solitary. Every push comes with a partner push. Every force has its twin. It's in the steps you take each day. When you walk, your foot presses down and back against the ground, and the ground, in turn, pushes you forward. Without the ground's reply, you would go nowhere, flailing helplessly. Motion is not just about you, it's about the world's answer. Scientists still marvel at how universal this law is. Rockets lift off the Earth not by pushing against the air, but by expelling gases downward at great speed. In reply, the rocket is thrust upward, away from the launch pad. Fireworks burst because gases rush outward. The casing recoils inward. Even the stars themselves, burning with fusion, balance forces in endless exchange. It's a law of symmetry, a law that says the universe is not unfair. No action goes unbalanced. There is something comforting here, isn't there? That you cannot act alone. That motion, effort, even the smallest push of your finger against a wall is always answered. The world notices quietly and responds in kind. And beyond physics, people have long found a metaphor here too. That every action ripples outward, that every cause invites an effect. Push kindness into the world, and something kind pushes back, though not always where or when you expect it. You drift now above Earth, watching the jet of a rocket flare downward, fire streaming into the night. In reply, the rocket glides upward, steady, unstoppable. Push and response, equal and opposite, written into the stars. The law doesn't shout. It doesn't demand equations tonight. It simply says, the world is balanced. No push goes unnoticed. No motion exists in isolation. So rest with that thought. When you breathe out, the air presses back in. When you lie on your bed, the bed presses up to hold you. You are not falling, you are answered. Newton's third law is not only physics, it is reassurance. A symmetry that hums beneath every step, every flight, every orbit. For every action, an equal and opposite reaction. For every push, a reply. For every effort, balance. The river and the boat fade into calm ripples, and now you drift back once more to that orchard, where the simplest of sights gave rise to the grandest of questions. An apple falling quietly from a tree. You've already pictured it before, the apple's stem weakening, gravity tugging gently until the fruit lets go, tumbling downward with a soft thud. But Newton's genius was not in noticing the apple fall. Everyone had seen apples fall. His genius was in connecting the ordinary to the extraordinary. If the apple falls to the ground, why does the moon not do the same? Why doesn't it tumble from the sky and crash into earth? The answer, Newton realized, was that the moon is falling. Constantly. Every moment, gravity pulls it toward earth, just as surely as it pulls the apple. But the moon has another motion too, its sideways motion, always carrying it forward. And so, instead of striking Earth, the moon curves around, endlessly falling, yet endlessly missing. You drift now between the orchard and the night sky, as if Newton's gaze has lifted upward. In one hand, an apple. In the other, the shining arc of the moon. Both obey the same pull, the same law. This was revolutionary. For centuries, people had divided the heavens and the earth. Apples and stones obeyed one set of rules, planets and stars another. The earth was seen as lowly, the heavens as perfect. But Newton saw unity, the apple and the moon, the orchard and the cosmos, one law tying them together, Scientists still wonder at the simplicity of that leap. To take something so homely, so ordinary, and connect it to the grandest scales of existence. It reminds us that deep truths often hide in plain sight, waiting for the right question. And though the story has been polished into legend, its meaning remains powerful. The apple is not about a sudden strike of genius. It's about patience, curiosity, the willingness to look at something everyone else takes for granted and ask, what if? You drift closer to the moon now, its pale light washing across the orchard fields. Imagine it arcing silently above, its path curved by gravity's pull. The same pull that drops fruit into grass. The same pull that guides tides, bends rivers, holds you gently to the earth as you lie resting now. Gravity is everywhere, silent and constant. You don't notice it until you stop and ask, why down, why not up? Why not sideways? The apple falls, the moon curves, and suddenly the two are the same story. So tonight, let yourself linger in that orchard once more. The air cool, the stars faint above, the apple tumbling softly in the dark. Let the connection sink in, that the smallest motions under your feet and the vastest motions overhead are written by the same hand, described by the same gentle law. And in that realization lies a comfort, that the universe is not divided or chaotic. It is whole. It is one. The orchard fades into twilight, and you drift upward now, beyond the fields and cottages of Woolsthorpe, into the quiet night sky where Newton's thoughts so often wandered. There it is. The moon, pale and steady, tracing its familiar arc above the earth. Newton imagined it not as a fixed lantern in the sky, nor as a body held in place by invisible strings, but as something simpler, stranger, and far more beautiful. A constant fall. Picture this. If the earth were flat and you tossed a stone, it would arc and land somewhere not too far away. Toss it harder, and it would go farther. Harder still, farther yet. Newton asked, what if you threw it so hard that, instead of hitting the ground curved away beneath it? The stone would fall forever, not down to the earth, but around it. That is orbit. The moon, he realized, is falling toward Earth every moment, but its sideways motion keeps it from colliding. It curves, endlessly missing, endlessly falling. The apple drops into grass. The moon drops into space, circling us in a gentle, endless embrace. You drift alongside it now, feeling the balance. Gravity pulls inward, motion carries forward. Together, they create a curve so graceful it has lasted for billions of years. The moon is both captive and free, always bound, always gliding. Scientists still wonder how to best explain this balance. Some use mathematics, sketching neat diagrams of centripetal force. Others prefer words. The moon is a falling apple that never lands. Both descriptions are true, both whisper the same principle. And beyond the poetry, the moon's motion shapes life on Earth. Its steady pull stirs the tides, guiding the rise and fall of oceans. It keeps Earth's axis steady, calming the wobble of seasons. Without the moon's quiet curve, our world would be less stable, less gentle. So you drift now along its orbit, looking down on the Earth below. Oceans gleam, continents sleep in shadow, clouds curl softly. All of it held together by the same law that drops an apple to the ground. It's comforting, isn't it, that something so vast is guided by something so simple. No hidden strings, no complex machinery, just the steady pull of gravity and the quiet persistence of motion. And perhaps, as you rest tonight, you can take comfort in that rhythm. That even falling can be graceful. That even something drawn inward can keep gliding outward, balanced, steady, serene. The moon curves, the earth spins, and you drift gently in their company. The moon's curve fades into the dark, and now you drift into the law that tied it all together, Newton's law of universal gravitation. Not just apples, not just the moon, but everything, everywhere, pulling on everything else. Newton's insight was astonishing in its simplicity. Every mass attracts every other mass with a force proportional to their sizes and inversely proportional to the square of their distance. That's the formal phrasing, but you don't need to cradle the equation tonight. Think of it instead as the universe whispering, everything pulls on everything. The apple pulls on Earth, and Earth pulls on the apple. The moon pulls on Earth, and Earth pulls on the moon. The sun pulls on the planets, and they pull on the sun. Even you, lying here, pull faintly on the stars above. A tug so small it could never be noticed, but real nonetheless. You drift now through the solar system, watching the planets in their stately paths. Mercury close to the sun, Venus veiled in clouds, Earth shining blue, Mars red and dusty. Each orbit is a conversation. Forward motion trying to escape, gravity calling it back. The two balancing into endless circles and ellipses. Newton's law did not just explain the moon. It explained tides, as the moon's pull stretches Earth's oceans. It explained comets arcing in long loops, their tails whispering against the void. It explained why Saturn's rings stay in place, why Jupiter's moons dance around it, why even the farthest planets hum in rhythm with the sun. Scientists still wonder at the audacity of this leap. Before Newton, the heavens and earth were seen as separate realms. Apples fell, planets circled, 2 stories, 2 sets of rules. Newton unified them into one, a single law describing both. It was as if he had pulled down the stars and set them in the same orchard with the apples. You drift closer now to Earth's oceans, watching waves swell and recede. The tides breathe in and out twice a day, pulled by the moon, steadied by the sun. Gravity is not just distant and abstract. It moves the water at your feet. It shapes the rhythm of the shore. And beyond Earth, it shapes galaxies. Stars circling centers, clusters bound together, the very cosmos woven by gravity's threads. The same law that tugs an apple downward holds galaxies in their spiral arms. There is a profound gentleness in this. Gravity doesn't roar. It doesn't spark or crackle like fire or lightning. It whispers, constant, patient. The weakest of nature's forces, yet the one that never lets go. So rest in that thought. Everything pulls on everything. You are not separate from the cosmos. You are tied to it, faintly, invisibly, by the same law that keeps the moon aloft and the planets in motion. The apple falls. The earth holds. The sun binds. And you, too, are part of the quiet pull. The oceans ebb and flow beneath you, their tides tugged gently by the moon. And now you drift higher, where the planets circle like patient hands on a cosmic clock. Newton's law of gravitation had shown that the same pull binding apples to the Earth also guides Mars in its orbit, Jupiter in its sweep, and Saturn with its glittering rings. Suddenly, the heavens were no longer mysterious fires moving in unknowable patterns. They were orderly, predictable, like gears turning in a vast, silent timepiece. You float now above the solar system, watching it in slow motion. Each planet moves at its own pace. Mercury hurrying around the sun in just 88 days. Saturn taking nearly 30 years for one lap. Neptune lingering for more than a century and a half. Yet together, their paths form a harmony, a rhythm steady enough that astronomers could set their calendars by it. For Newton, this order was proof of something profound. The universe was not chaos, not capricious, not governed by whims of gods or demons. It was a cosmos governed by law. Imagine being an astronomer in the 1600s, peering through a telescope polished with care, noting the position of Jupiter's moons night after night. Before Newton, the data was impressive but disconnected, like notes without a melody. After Newton, the tune revealed itself. Gravity keeping perfect time, turning the heavens into a vast celestial clock. Scientists still wonder at the elegance of it. With a single law, Newton tied together Kepler's careful measurements of planetary ellipses, Galileo's falling bodies, and the moon's endless curve. Equations that once seemed separate became variations on the same theme, the universe ticking steadily forward. You drift past Saturn now, its rings glinting faintly in sunlight, icy particles orbiting in perfect balance. Each fragment of ice, no matter how small, obeys the same rules as stars and planets. Even dust, even pebbles, fall into rhythm. And here's a comforting thought. If the cosmos is a clock, then time itself is woven into its order. Day and night, tides and seasons, eclipses and returns of comets, all predictable, all serene. Newton's laws gave humanity not just knowledge, but reassurance. The sky is steady. The future can be measured. The world is not arbitrary, but bound by rhythm. You hover above Earth once more, looking down at a sundial casting its shadow. The slow creep of shadow across stone is the same motion that carries planets across constellations. One law, one timepiece, different scales. It's almost musical, this vision. Planets as notes, orbits as measures, the sun as conductor. The solar system plays on, calm and unhurried, a lullaby too vast for human ears, but soothing all the same. So rest in that image. The sky as a clock, the cosmos as a song, each apple, each orbit, each tide a part of the same rhythm. And tonight, your own breathing joins it, steady, regular, another tick in the quiet clockwork of the universe. The orbits and the great celestial clock fade softly into the background. And now you drift toward the book where Newton gathered his thoughts, his equations, his vision of a lawful universe. It was called Philosophiae Naturalis Principia Mathematica, or simply the Principia. Published in 1687, it was not light bedtime reading. Dense Latin, long proofs, diagrams sketched in neat lines. And yet, within those pages, lay a revolution so quiet and steady it reshaped the world. You float now above an old printing press, its gears creaking, ink staining thick paper. The Principia emerges sheet by sheet, bound together into a volume that would soon travel across Europe, into the hands of scientists, philosophers, and dreamers. Inside were Newton's 3 laws of motion, laid out with calm certainty. Inside was the law of universal gravitation, connecting falling apples to circling planets. Inside was a vision of the cosmos not as chaos, but as order, a grand machine ticking according to simple, universal rules. The book was heavy with mathematics, but it was also filled with quiet beauty. Newton showed that the curve of the moon, the tides of the oceans, the sweep of comets, the fall of stones, all could be written with the same language. For the first time, heaven and earth were united in one system. Scientists still wonder at the patience it must have taken. Newton worked in solitude, shaping arguments with rigor, refusing to publish, until pressed by friends like Edmund Halley, who not only encouraged him, but even paid for the printing. Without Halley's persistence, the Principia might have remained scattered notes in Newton's drawer. And what a loss that would have been. You drift now through the pages, the ink forming familiar words: lex prima, lex secunda, lex tertia. First law, second law, third law. The very rhythm of motion captured on paper. The book was not easy to read. Few could grasp its full depth, but its effect was profound. Astronomers used it to refine predictions of eclipses and orbits. Engineers used it to build bridges and machines. Philosophers used it to imagine a universe governed not by chance or divine whim, but by steady law. The Principia became more than a book. It became a foundation, a cornerstone of modern science. And yet, Newton himself was not eager for fame. He guarded his ideas fiercely, argued stubbornly with critics, but often preferred solitude to applause. His brilliance was wrapped in silence, his greatest work produced not for praise, but because the questions would not let him rest. You hover now over a candlelit desk, the pages of the Principia spread before you. Outside, the night is still. Inside, the universe has just been rewritten. It's humbling, isn't it? That the vast motions of planets, the endless tides of galaxies, could be traced back to the scratch of a quill on parchment, to the patient work of one man, alone with his thoughts. And perhaps that's the quiet lesson tonight, that even the heaviest books begin with a single question. Why does the apple fall? Why does the moon curve? What holds the cosmos together? Newton asked. He answered. And the answers became a book that changed the world. The candlelight on the Principia fades, and now you drift into the echoes that followed its publication. For not everyone was ready to embrace Newton's vision. Change, even when written in elegant equations, rarely arrives without resistance. Imagine the Europe of the late 1600s. Scholars in wigs and long coats, debating in lecture halls and coffee houses. Letters carried across countries to argue over ideas. Some received Newton's laws as revelations, clear and undeniable. Others furrowed their brows. Invisible forces, action at a distance. It all sounded suspiciously mystical. You float now into one such hall. A professor stands before a chalkboard, insisting that objects cannot possibly affect one another without something touching them. To him, motion requires contact. A hand pushing a cart, air pressing against wings, water moving a boat. Gravity, as Newton described it, was invisible, a pull across emptiness. How could that be real? Hypotheses non fingo, Newton replied. I frame no hypotheses. He would not pretend to know why gravity worked, only that it did. He did not explain its mechanism, but he showed its laws. Apples, moons, planets, the evidence was enough. This, for many, was unsettling. To admit that something invisible, intangible, could govern the cosmos felt like surrendering to mystery. Yet Newton's predictions were so precise that the resistance could not hold forever. Scientists still wonder how deeply this discomfort shaped the next centuries. Some critics clung to the idea of an ether, a subtle medium filling space, a way to make gravity less ghostly. Others embraced Newton's silence, accepting that not all answers were yet knowable. And even among admirers, debates raged. Was Newton's universe truly a clockwork, perfectly wound? Or might hidden irregularities someday appear? Would comets disrupt planets? Would friction eventually slow the heavens? Questions piled as fast as admiration. You drift now above a coffee house in London, where pamphlets lie scattered on tables. Scholars lean in close, voices low, trading arguments over Newton's Latin prose. Some declare him a genius, others a dreamer. Some predict the Principia will last centuries, others suspect it will fade. But history chose its side. The predictions held. Eclipses occurred as Newton calculated. Tides followed his equations. Comets returned on schedule just as Halley had promised. Slowly, the doubts quieted. Still, the resistance is worth remembering. Because even the most elegant truths often arrive wearing a cloak of strangeness. At first glance, they look implausible, unsettling, even absurd. And only with time, with patience, do they reveal their beauty. Perhaps that is a lesson for tonight. Not all mysteries need instant acceptance. Some truths take years, even generations, to be seen clearly. You drift now between Newton's supporters and critics, hearing their voices fade into the past. Both were necessary. Admiration pushed the work forward. Skepticism tested it, sharpened it. Debate, too, was part of the process. And through it all, Newton remained steady, sometimes stubborn, but certain that his laws described the world as it was. He did not claim more than he could show. He simply wrote, calculated, observed, and let the universe speak for itself. The pushback fades, the debates quiet, and what remains is the law, gravity, motion, inertia, still holding apples, moons, and planets in place. The debates in coffee houses fade into the hush of night, and now you drift into a quieter, stranger corner of Newton's life, the part less often told in classrooms. For behind the pages of the Principia and the neat laws of motion, there was another Newton, one who filled notebook after notebook with secrets, symbols, and recipes not of science, but of alchemy. Picture him at his desk, candle flickering, ink stains on his fingers. Not scribbling equations this time, but strange mixtures. Mercury, sulfur, salts, powders. He copied ancient texts, sketched diagrams of furnaces, and experimented with substances in search of the philosopher's stone, that legendary key said to transform base metals into gold or grant hidden knowledge. To us now, it seems fanciful, even absurd. But in Newton's age, the line between alchemy and chemistry was thin, blurred. Alchemy was not only about wealth. It was about uncovering the hidden structure of nature, believing that matter carried secrets waiting to be revealed. You drift closer to his shelves, stacked with bottles and jars, powders and minerals, some dangerous, some harmless. Newton inhaled vapors that likely harmed his health, stirred concoctions that stained his hands, and recorded the results in a code only he could read. Why would a man of such clarity, who gave us precise laws of motion, immerse himself in something so shadowy? Scientists still wonder. Some think he was simply a child of his time, blending curiosity with tradition. Others suggest he saw alchemy as a way to uncover truths that mathematics alone could not reveal. But perhaps there is a gentler answer. Newton was not only a scientist, he was a dreamer. He wanted to see beneath the surface of things, whether through prisms splitting light, or formulas binding planets, or crucibles glowing in the night. For him, the world was full of secrets, and he would not stop looking. And alchemy, in its way, gave him metaphors too: transformation, hidden forces, matter changing its form under heat. These images may have shaped the way he thought about gravity and motion, not as visible contacts, but as invisible threads binding the universe. You drift now into his private notebooks, where symbols twine across the page, half scientific, half mystical. It is a reminder that genius is rarely tidy. Newton contained contradictions. The rational mathematician and the secretive alchemist, the public scientist and the private dreamer. And maybe that, too, is comforting. That brilliance does not always arrive in straight lines. That searching in odd places, even mistaken ones, can sharpen the mind for greater discoveries. So let yourself rest in this image. Newton at night, candlelight flickering, one hand steady on his pen, the other reaching toward mysteries that even he could not solve. For in the end, he was not only a man of laws, but of wonder. And perhaps that is why his story still hums softly through time. The flicker of alchemical candles fades into the broader daylight of history, and now you drift into the centuries after Newton. His 3 laws and the pull of gravity had left his desk, his notebooks, his orchard, and had spread across the world. The legacy of motion was no longer only an idea. It became the foundation for bridges, ships, machines, and eventually rockets that would leave Earth itself. Imagine an engineer in the 1700s, blueprint spread across a wooden table. The laws of force and motion guide the span of a bridge, the sweep of an arch, the strength of a support beam. Builders could now calculate with confidence instead of guessing. Structures grew taller, stronger, steadier, as though Newton's equations were hidden inside their stones. You drift next to the sea, where ships cut across the water. Navigators watch the stars, predicting tides with Newton's formulas. Cannonballs arc from decks, their paths described exactly by mass, velocity, and force. War and trade alike were guided by his laws. Then forward again into the 19th century, where the Industrial Revolution hums with steam and steel. Locomotives thunder along rails, pistons push and pull, engines churn. Every gear turning is an echo of Newton's second law, force shaping acceleration, motion answering push. And finally, the 20th century. Rockets rise into the night, their engines roaring, each action answered by Newton's third law. Exhaust pushed downward, rocket lifted upward. Satellites slip into orbit, their curved paths repeating the same lesson as the moon's fall. Astronauts float in weightlessness, inertia carrying them until a small push redirects their path. Scientists still marvel that Newton's equations, written with quill on parchment, still guide spacecraft across millions of kilometers, steering them with precision toward distant planets. No matter how advanced technology becomes, the foundation remains. Push, pull, mass, acceleration, balance. You drift now through a classroom, a chalkboard filled with scribbled formulas. A student pushes a toy car, watching it roll. Another balances on a skateboard, noticing how pushing backward moves them forward. Newton's laws are taught not only with mathematics, but with play, with examples anyone can feel in their bones. And perhaps that's the secret of his legacy. The laws of motion aren't abstract. They are lived every day. The way you steady yourself on a bus, the way a swing carries a child forward, the way footsteps press against the ground. The universe's rules are written into your very movements. The legacy of motion is not only in grand machines or spaceflight. It is in the simple comfort that the world is knowable. That causes have effects. That pushes have replies. That gravity will still be there tomorrow, steady as always. So tonight, let yourself rest in that legacy. Your breath in and out, inertia carrying air through your lungs. Your body on the bed, gravity holding you gently in place. The universe, vast and quiet, obeying the same laws Newton once wrote by candlelight. The legacy of motion is not only history. It is the present moment, holding you now. The bridges and ships, the rockets and classrooms fade behind you. And now you drift into the quiet conclusion of Newton's story. Not a single event, not a single discovery, but a vision. the picture of a universe that moves like clockwork. For Newton, the cosmos was not chaos, it was order. Apples fell, moons curved, tides swelled, planets orbited, all under the steady rhythm of a few simple laws. Nothing was random. Nothing without cause. Every push had its answer, every orbit its equation, every fall its reason. You float now above the solar system once again. The sun glows at the center. Planets sweep in arcs, steady and serene. Comets trace long ellipses, returning after decades or centuries, always on schedule. The universe ticks softly, like the turning of gears in a great cosmic clock. Scientists of Newton's time and after found comfort here. A world governed by law was a world that could be trusted. Not capricious, not dependent on unseen whims, but steady, calculable, ordered. Astronomy became prediction, not mystery. Engineering became design, not guesswork. Even philosophy bent toward certainty, imagining the universe as a vast machine wound up at creation, ticking calmly ever after. And yet, Newton himself was not a simple clockmaker. He believed the order of the world pointed to something greater, something beyond human understanding. His laws described how, but he still wondered why. That question, perhaps, remains with us all. You drift closer now to the earth, looking down at oceans and forests, mountains and cities. Everything you see is cradled by gravity, moved by inertia, balanced by equal and opposite forces. From the smallest pebble to the largest star, the same laws hold. Scientists still wonder at how far Newton's vision can stretch. Later centuries revealed cracks at the edges, relativity, quantum mechanics, newer theories that complicate the neat gears of the clock. But even now, Newton's laws remain the first foundation taught, the ones still guiding rockets, still building bridges, still shaping the rhythm of the everyday. And perhaps that is the most comforting truth. For all the complexity of modern science, the basics remain simple enough to hold in your mind. Things move unless stopped. Force changes motion. Every push has a reply, and gravity pulls us all together. So tonight, let yourself rest in Newton's universe. A cosmos that is not hostile but steady, not chaotic but rhythmic. A clock whose ticking is too slow for ears, but gentle enough to lull you into sleep. The apple falls. The moon curves, the planets circle, the stars turn. And you too move within that same quiet law. And now the story of Newton settles into silence. The orchard is still. The apple has long since fallen. The moon curves on, steady in its endless path. You've drifted through his life, his laws, his visions, and what remains is not the mathematics, but the calm rhythm of motion itself. Take a slow breath in. Hold it gently. Let it go. Just as Newton taught, your body is at rest, and it will stay at rest. You don't need to push. You don't need to force. The bed beneath you holds you softly, gravity's quiet pull keeping you safe. The universe moves on, but you don't need to keep pace. You are allowed to pause, to surrender to stillness. The laws of motion will carry on without you. The planets will circle. The earth will turn. The apple will fall. You are free to rest. Imagine the cosmos as Newton saw it, a great clock ticking slowly, patiently, without hurry. Each star, each planet, each orbit another gear turning with perfect rhythm. And you, a part of that clockwork, not separate, not forgotten, but gently included in its design. Your thoughts drift like satellites, circling for a moment, then fading. Your breath slows like tides, rising and falling under a steady pull. Your body sinks deeper into stillness, at rest until morning's nudge. You don't have to solve problems now. You don't have to carry questions. You only have to let go. The universe is steady. The night is kind, and sleep is waiting, so close your eyes a little heavier. Let motion slip into stillness. Let thoughts slip into dream. You are safe in Newton's gentle universe. The clock is ticking softly, and you are already drifting.